Hello, this is Mr. White, and this video is on using antiderivatives or indefinite integration to analyze some freefall motion exercises. I will mention that the first of these two exercises is pretty straightforward, and I'm going to go through it fairly quickly. Students usually don't have too much trouble with that. It's the second one that causes more problems, so that's the one we'll slow down and do in more detail. So let's get into that first one. All right, you've been spending a lot of time on the moon lately. Not sure why, kind of strange. And you're throwing rocks upward at lunar cliffs, even stranger, but I'll stop judging. Let's start analyzing this problem by getting down our initial conditions. So when you throw this rock, it leaves your hand 6 feet above the ground level, and that is our initial position, right? So at time t equals 0, right when you start the stopwatch, at t equals 0, the position or height is 6 feet. All right, we are told that the initial upward velocity is 80 feet per second. So the velocity at time t equals 0 equals positive 80 feet per second. If I was on top of a cliff throwing downward, I would make that negative 80 feet per second, right? Oops, I forgot the per second. But in any case, this is going upward, so we'll change it back to positive 80 feet per second. And finally, we're told that the acceleration is negative 5.3 feet per second squared. So the acceleration is going to be negative 5.3 feet per second per second. All right, now I'm not going to put a 0 inside this parentheses. I could, and it would be a true statement. The acceleration is negative 5.3 feet per second when t equals 0. But it turns out that we're going to treat it as constant. It's going to be negative 5.3 feet per second for all values of t. So we'll make the more powerful statement, a of t equals negative 5.3 feet per second squared. And having just mentioned those assumptions, I should have brought up earlier, we are assuming this constant acceleration as well as the typical assumptions of we're going to neglect any air resistance, which is actually not a bad assumption on the moon where there is no atmosphere. And we're also going to just focus on the vertical velocity. Notice that in the problem statement, words like upward and downward emphasize that we're focusing only on the vertical components. We're not going to worry about any horizontal motion of this rock. All right, so now that we've got our initial conditions down, let's get into the antideriving. And I should point out that you can only either derive or antiderive functions that are true for all values t. Such as a of t right here. That's what we're going to antiderive. You would run into trouble right away if you tried to either derive or antiderive either this position or velocity equation because they're only true at an individual point in time, not all values of t. That's a point you definitely want to ask for clarification on if what I said didn't make sense. All right, so since acceleration is the derivative of velocity, then velocity must be the antiderivative of acceleration, right? So that's what we're going to say here. The velocity is a function of time. The general velocity equation will be the antiderivative or indefinite integral of acceleration, dt. And in this case, that is the indefinite integral of negative 5.3. The units are understood to be the imperial units, feet per second squared, dt. And when I go ahead and antiderive that, we get negative 5.3 t. Now, we normally put plus c, right? However, in this case, I think you'll pretty quickly see, if we haven't already discussed it in class, I hope this makes sense, that the constant of integration we're going to put is v sub 0, just to clearly represent that that is our initial velocity. And in fact, when you plug a 0 into that equation, for v of t, and you plug in a 0 for this t over here, you see that that term goes away. And again, this should make sense that v of 0 equals our initial velocity. Now, since we were given the initial velocity over here, right? We're given the initial velocity. Let's go ahead and plug that in. Equals negative 5.3 t plus 80. There it is, our velocity equation. So let's keep on antideriving. Let's now say that since velocity is the derivative of position, position, s of t, must be the antiderivative of velocity. So the indefinite integral or antiderivative of v of t, dt, which we just determined is negative 5.3 t plus 80 dt. And when we antiderive that, we get negative 5.3 over 2. I could calculate what that is, but I'll just choose to leave it as negative 5.3 over 2 times t squared. That is the antiderivative of the first term, plus 80t, antiderivative of the second term. And using similar reasoning as we did just a moment ago, instead of doing plus c, we'll put plus s sub 0. And this time, just to save a little time and space, I've already got s sub 0 over here, so I'm just going to erase that s sub 0 and go ahead and plug in the 6. So there is our position equation. All right, now as far as answering the ultimate question we're asked about what is the downward velocity when it impacts this cliff 300 feet above the ground, we certainly could do that algebraically. And it's not a bad idea to practice those algebra skills. We could certainly set this position equation equal to 300. We would expect two roots. When the rock is going upward, it should reach the 300-foot mark, and then it should reach 300 feet again, coming back downward. So we have to be sure to get the second root, the greater time value. And we could take that time value and then plug it into our velocity equation right here, right? However, I'd like to just exercise our calculator skills, because sometimes that's something that students neglect. So let's bring the calculator onto the screen here. I've already typed in that position equation. Of course, we'll conceptualize that x as being t. And as far as our window settings goes, I often find students fumbling around trying to figure out, just doing a lot of guess and check to figure good window settings. I'll remind you that you can look at the table. Let's go to the table and get an idea of what kind of numbers we're dealing with. So here we see, remember the x column will conceptualize as t for time, and the y column will be our position. And as expected, this ball is rising from an initial position of 6 feet, getting higher and higher and higher. And the table is a good way to kind of get a sense of how high it will go before it comes back down. And I see that right there around 15 seconds or so, it's just surpassed the 600-foot mark and it's coming back down. And I'm really interested in it getting to 300 feet, which looks like it occurs somewhere around 25 or 26 seconds. Things take a long time on the moon there to fall, don't they? If I really wanted to, if I was interested in what about when the ball comes down and hits the ground, or the rock comes down and hits the ground, it looks like that would happen around 30 seconds or so. So looking at the table gives me a quick idea that for my window settings, let's say that we're interested in a time from 0 to, let's go ahead and put 32 seconds or so. And we're interested in getting up to about 600 feet, a little bit over 600 feet. So let's go ahead and say 700 for our y max, and let's count by 100 on the y scale. And again, doesn't really require much guess and check. We get a pretty good graph right off the bat here. Now, again, I'm interested, let me point out too, that if I trace to 0, I get the expected initial position of 6. And as far as the initial velocity, let's just confirm, if I go to second calc and then number 6, dy over dx, that should give us our velocity, right? So let's hit enter, and then at 0, we'll hit enter. And sure enough, the slope at that point is 80. That's our initial velocity. So we're interested in when this reaches a 300-foot cliff. So let's put in 300 for our y2 and go ahead and graph that. And I'm not interested in when it reaches 300 on the way up. I'm interested in when it reaches 300 on the way down. So I'll go to second calc, number 5, intersect. And first curve, enter. Second curve, enter. A reminder, you don't need to waste time messing with the cursor at that point. Here's where you mess with the cursor when it says guess. Make sure that the cursor is closer to the second point of intersection. And I'll hit enter. And there is our point of intersection. Looks like at 25.9 seconds or so, that's when the ball or the rock comes back down and touches the cliff, 300 feet high. Reminder of some calculator techniques. I'm going to go to second quit, and I'm going to take that x value that was just calculated, and let's stow that as a little bit more permanently as alpha t. And that way I can refer to that t in a later calculation, as I will do right now. So let's go back to the graph, and let's go to second calc, and let's calculate the derivative. I'm just going to press the number 6 for dy over dx. Let's calculate the derivative. And I'll remind you that although it looks like the calculator has gone back to that point of intersection, it jumps off a little bit. That value displayed right now, unfortunately, is not the one we just calculated. That's why I'll go to alpha t and get the precise value we just calculated a moment ago. And that is the more precise velocity at that point. So let me drag these on here. Go back here and remind myself what that time was. And what that's telling us is that at the velocity at 25.9 seconds or so, and I'm going to use the AP convention of 3 decimal places, even though a physics nerd would laugh at that, is about, let's see, we said right here, negative 57, again, 3 decimal places, 303 feet per second. That's how fast the rock is coming downward at the time of impact with the cliff. All right, hope that made sense. I repeat, we could have done that all algebraically, not graphically, but I wanted to review some efficient calculator techniques. All right, let's go on to the second exercise. All right, you're standing on top of the Superdome for some reason, 273 feet tall, and you throw a ball into the air which just reaches the height of 1 shell square at its maximum. That's the tallest building in Louisiana, by the way, at 697 feet tall. We're going to assume our constant acceleration, negative 32 feet per second, and we are to find the initial vertical velocity, how long it takes to reach the ground, the ball to reach the ground, and what is the vertical velocity of the ball upon reaching the ground. We're going to make several assumptions here to make our life a little easier. Again, we're going to assume the constant acceleration of negative 32 feet per second. As usual, we're going to neglect air resistance, which if I can remember at the end, I'll say a quick word as to whether that's a reasonable assumption or not. Sometimes you find it isn't reasonable, and then the math gets a lot harder at that point. We're going to assume that the ground level is 0 feet per second for both structures. We know, given the geography of Louisiana, or New Orleans in particular, that may or may not be true, but we're going to assume that for this case. And we're also going to assume that there's enough of a horizontal component to this ball such that it clears the Superdome. Obviously, if we throw some ball straight up in the air until it reaches the same height as the shell tower, and if it comes straight down, it's not going to touch the ground first. It's going to bounce along the Superdome and then maybe bounce onto the ground. Well, we're going to assume that there's enough of a horizontal component such that the ball reaches the height of the shell tower, and then when it comes back down, it clears the Superdome. We're not going to try to analyze that horizontal component. You've been given no information about it. We're just going to analyze the vertical components, but we'll assume that the ball does clear the Superdome. All right, and one more quick word before we jump into this. Every year I have students who are taking AP Physics concurrently with AP Calculus, and they want to use this equation because it makes their life so much easier. I admit that it does, but of course I'm going to spoil the party and say you're not allowed to use this. First of all, most AP Physics students can't tell me where this came from, which is disappointing. I look at it and I see some conservation of energy in there. Your AP Physics teacher may have told you, taken some different route to get there, but regardless of where it came from, or if you understand where it came from, you're not allowed to use it in AP Calculus. You need to rely on your antideriving or indefinite integration skills. Okay, so let's jump into it. And let's, of course, start with our initial conditions. You're standing on top of the Superdome, 273 feet tall. So initial position, the position at time t equals 0, we're going to say is 273 feet. Now, granted, when you throw a ball, you're not throwing it from foot level, so you could argue that the height of the person throwing the ball should be factored in, but we weren't given that information, and when you're dealing with heights this big, in the hundreds of feet, the height of the person throwing the ball is going to be, we could probably make an argument that it's just negligible. So let's go with initial position is 273 feet. Let's see, initial velocity is, well, we don't know initial velocity. That's one of the things we're supposed to find out, right? So we don't know that. However, we do know that the acceleration, again, not just the initial acceleration, but the acceleration at all times t, we're going to say is negative 32 feet per second, or feet per second squared. Okay, now we're not completely done here. We've also been given some information, not just for the initial time, but also at the, about the maximum height. Let's go ahead and say that at the maximum height, this ball is at 697 feet tall. So that's S equals 697 feet tall. Now, we don't know what time, we don't know how long it takes to get to that 697 feet. That's an unknown. So I'm going to put a variable in there, t sub m, m for maximum. You can, choose whatever variable you want, but I'm going to use t sub m to represent the time it takes for the ball to reach its maximum height. Now, can you think of what's one last equation we can write here that we haven't already written? What about its velocity at the maximum height? What's the velocity going to be? Well, at whatever time that t sub m is, if it's at its maximum height, we know the velocity is going to instantaneously be 0 feet per second. So there they are. There are our initial conditions. So just like last time, the only quantity we have here that is a function of time is acceleration, a of t. A of t equals negative 32 feet per second squared, so that's what we're going to start antideriving. We antiderive that to get velocity as a function of time. So v of t, velocity as a function of time, equals the antiderivative of a of t. And this time, just to save a little time and space, I'm just going to go ahead and plug the negative 32 feet per second squared in there instead of writing a of t. And we'll go ahead and antiderive and get negative 32t. And this is where you normally would put plus c, but I'm going to put plus v sub 0 because hopefully you understand now that that constant will always represent our initial velocity here. So let's go ahead and antiderive that now. Just like we did in the last exercise, let's antiderive velocity to get position. Position s of t equals the indefinite integral of that velocity that we just wrote down, negative 32t plus v sub 0 dt. And that's going to give us, let's see, negative 16t squared. That's the antiderivative of negative 32t, right? Plus v sub 0 times t. Remember, even though we don't know what v sub 0 is, we know that it's a constant. So when you antiderive a constant, you get that constant times the variable t in this case. Okay, and then we've got our plus c, which in this case we'll write as plus initial position s sub 0. Now remember, we actually know in this case, we didn't know what initial velocity was, but we do know initial position is 273 feet. So again, to save a little bit of space, I'm just going to erase that and put 273. So there is our position equation. And the only thing we don't know about it is the initial velocity. And how are we going to get that? Well, that's where this information about the maximum point of travel is going to help us out. Those initial conditions are going to help us solve for v sub 0. So let's go ahead and plug in. Let's go ahead and plug in t sub m. Let's say that this initial position, s of t, sorry, that's not initial position, that's the position at maximum time, right? So s of t sub m equals negative 16 t squared, and that's t sub m squared, right? Plus v sub 0 times t sub m. We'll also, when we solve for v sub 0, we'll also be solving for t sub m, as you'll see, plus 273. And we know that at that time, when I plug in that t sub m, I better get 697 feet. So let's set that equal to 697. Now notice that you cannot solve for either of those unknowns at this point. You've got a single equation right here in green with two unknowns, v sub 0 and t sub m. So you know that when you have two unknowns, you need two independent equations. And that's where this last initial condition is going to come in. So let's take that v of t sub m equals 0 feet per second. And let's plug it into this equation for v of t. Okay? So v of t sub m equals, let's see, negative 32 t sub m plus v sub 0. I'm getting that from up here, right? And then I'm going to set that equal to 0 feet per second. And here we have our system of equations. Two independent equations, with both of which have the same two unknowns, v sub 0 and t sub m. You know what to do in this case. I'd suggest you maybe pause the video, soak all this in, make sure it all made sense. And if you feel up to it, go ahead and see if you can finish off the problem. If not, of course, I'll proceed here as well. So I'm looking at the system of equations, and I see the easiest route to solve for those unknowns is to, let's solve for v sub 0 in terms of t sub m here. Let's get the v sub 0 on one side, and it doesn't take much work to get that isolated. V sub 0 equals 32 times t sub m. And now we're going to substitute that into our position equation. We're going to substitute that into this equation right here, and that will give us a single equation with a single unknown. Go ahead and scroll down a little bit here, and let's rewrite that position equation. Negative 16 t sub m squared plus, now here's the substitution. Instead of v sub 0, I'll write 32 t sub m times t sub m plus 273 equals 697. We have a good fortune here. We see that we have two like terms. We've got negative 16 t sub m squared plus 32 t sub m squared, right? So those two combined would give us positive, again, these two combined would give us positive 16 t sub m squared. And let's go ahead and subtract that 273 over to the other side, and that'll give us 697 minus 273, or 424. Let's go ahead and solve for t sub m. Equals 424 divided by 16, and we'll square root that. That will give us, obviously we're only interested in the positive root. That's square root of 26.5, which is approximately 5.148 seconds. I'm now going to take that and I'm going to plug that into this equation up here. V sub 0 equals 32 times that 5.148 seconds times that t sub m. And that's going to give us about 164.730 feet per second. There are the two unknowns that we were looking for. We weren't explicitly asked for that t sub m, but we were asked for the v sub 0, and there it is. All right, before I forget to come back to this point, let's bring up our initial assumption about air resistance. We said that we're going to neglect air resistance, yet it turns out that this initial velocity, 164.73 feet per second, well, that's about 112 miles per hour, which is faster than a Major League Baseball fastball. So the idea that we're going to neglect air resistance is really a bit of a shaky assumption if we were to try to apply this analysis in a real-world situation. But we're going to move ahead and just acknowledge that we're on shaky ground here. The math and physics involved to properly address air resistance is beyond the scope of what we're trying to do here. So let's move ahead. Here is our position equation, and also a reminder of what it is we're supposed to be doing here in this example. We have found the initial velocity, and in fact, we can now plug that into our position equation. So let's move this aside, get rid of this v sub 0, and plug in the 164.73 that we just found. And let's summarize graphically what we have and what we still need to get. If we're graphing position with respect to time, we have a ball that has started at 273 feet tall, the height of the Superdome, and it has gone upward along some trajectory like that with respect to time. We have found that the initial velocity is about 164.73 feet per second, the slope of that line, right? That's our initial velocity. We have found that after about 5.148 seconds, after about 5.148 seconds, the ball has reached 697 feet tall. That's the maximum height of one shell square. And of course, at that point, the velocity is 0. The slope of that tangent line is 0. And what we have yet to find is the time to reach the ground as well as the vertical velocity upon impact with the ground. So we need to find what is this time right here and what is the slope at that point. So again, similar to the last exercise, we could do that algebraically. I'll acknowledge that we could do that. And we could set the position to 0, solve for t, which would give us that time there, and then plug that time into the velocity equation in order to get the velocity upon impact. But I will again choose to just exercise our calculator skills at this time. Realistically, on an AP exam, a problem of this nature would be in the calculator section. So let me bring the calculator on here. I've already done some things to save time. I've typed in that maximum time and stowed it as variable t. That's the 5.148 seconds. And then I've calculated the initial velocity and stowed that as v. Therefore, when I go to y equals, you see I've entered in that position equation. Of course, there's variable x instead of, we'll conceptualize that as being t for time, of course. And as far as our window settings go, if I move this to the side and look at the graph I just drew, I'll come up with some reasonable window settings. I would say that the numbers I've already entered here, pre-entered, are a pretty good idea, a pretty good guesstimate of what would be some good window settings. So let's go ahead and graph. And we get a graph like this, just as anticipated. We'll go to second calc 0. We want to find the second 0. So somewhere around there, I'll just hit enter. And I've got the x max set to 15, so I'm just going to type that in for my right bound and hit enter. And there is the time that it takes to impact the ground. So again, to exercise that stowing of variables, I'm going to go to quit. I'm going to say take that x value, stow it. Now I've already used t, and just in case I wanted to come back to that maximum height time again later, let me stow that as a different variable. I'll stow it as g for ground, 11.748. And then I'll go to the graph here, and I'll go to second calc dy over dx, number 6, at alpha g. Now you may be wondering, couldn't I just have written that number down and typed it in? You could have, but again, I'm trying to emphasize the stowing of variables, which I think in some cases can really be beneficial. And there is our velocity upon impact. Now that negative 211.2 feet per second, that's about negative 144 miles per hour. So again, our assumption of neglecting air resistance really is becoming problematic. But let's roll with it. That's what we said we would do. So coming back, we said that this time to reach the ground was about, this time right here was about 11.748. And again, I repeat, I'm using 3 decimal places per the AP conventions. Seconds to reach ground. And we said at that time, v of that 11.748. Again, we could have just plugged this into the velocity equation to get this result as well, would be approximately negative 211.206 feet per second. So again, that is what's going on when the ball hits the ground. All right, again, I emphasize one last time, we could have done all that algebraically, but I wanted to highlight some of the graphical aspects of that exercise as well. Hope that made sense.